The final library we're going to look at is the fixed point library. Now so far we haven't been able to represent decimal numbers. And in fact, we are going to introduce a floating point unit in the next course, and that will allow us to represent a much wider range of integers and decimal numbers. But for the moment, we're going to introduce something called fixed point. And we're really doing this as a learning mechanism just to show how fixed point number systems would work within our machine. So it's like a little kind of cameo of what we could potentially do with fixed point numbers. But we don't want to get into too much detail because it will be superseded by the floating point unit in the next course. In this course of videos, I have mentioned that I'm not going into all the details. If you're interested in all of the details of a fixed point number system and how I generate all of these subroutines, then it's all available within the Design a CPU 3 course. What we want to see here are just the calls to those subroutines and how we can use it. So let's start off by looking at add and subtract. The great thing is that the add and subtract, we don't really have to do anything. It just works the same as the normal addition and subtraction for our binary numbers. But there is one thing that we have to note here. We have to introduce the actual idea of a fixed point number into the assembler. So we do that by simply putting the letter F in front of a number. So if we've got a hash and an F, the assembler knows it's a fixed point number and it deals with it as a fixed point number. So for example, if we wanted to represent the number 10.75, we would put the value hash F 10.75. And if we're going to add these two numbers together, we should get the number 13 in hex. And if we were going to subtract both numbers, we should get this number here, 0801. Okay, so 13 in hex, it would be 0C and then 00. So that would be the full representation. Now all we do is, in this instance here, we could load the first number into register R0, the next number into register R1, and we can simply do the addition R0, R1, and it'll come out with the correct answer, as long as we put the value of F here in front of the numbers. Now if we're going to perform multiplication and division, there's a little bit more involved in it. And in fact, we have to write an algorithm in order for us to run the multiplication and division within our fixed point number system. But of course that's already been done and it's all been built in, and if you're interested in how we do that, you can see it within the full course. But all we're going to do for this here for multiplication is define the number. So we've got x in this instance here is f minus 10.75 and y is 2.25, and we push in this instance the value of x onto the stack, we push the value of y, we jump to the subroutine that does the multiplication. Okay, so this is a subroutine that has already been designed and it's inside the ROM, and if you want to see how that subroutine works, you can go and do the full course. So it works out the answer and it pops the answer into this location here called answer. So if this is right, we get the 10.75 times 2.25 should give us this number here, and that is this number here in hex. And I've put another example number here as well. So that's the multiplication. So the final one is a division, and again we have to run through a division algorithm which has already been done and it's loaded into the ROM. And again we can just push the value of x, push the value of y, and then jump to the subroutine floating fixed point underscore div, and that'll generate the division and it will save it in this ANS. And there's a couple of examples there. Now the next one that we're interested in, and I've decided to do, is the power function. Now I've decided to do the power function because it's really useful whenever we come to generate other mathematical functions using the Taylor series. And the Taylor series uses at its core a power function. So we've got the function ax to the power of n, and we've already seen this function before. We generated an integer version, so this here is our fixed point version. So we can simply push the value of a, push the value of x, push the value of n, and it will get through the subroutine and it will provide us with the result. And here's an example of shown below. Now the great thing and the reason for doing this power function, as I said, is that we can now go ahead and we can generate the sine, cosine and the tan function. So we can generate these using the Taylor series approximation, and that's what I've done within the assembly language. And again, if you're interested in the details of all of that code, you can go and take the Design a CPU 3 course. So this allows us to put a value in for x. Now it's any value in radians, and then it will generate the sine of that value, and it will return it to a memory location sine underscore x. Of course, it returns it in the fixed point number system, so in order to get the actual number, you've got to convert from the fixed point to the normal binary number system. And I have a couple of conversion tools which I will show you in a different video. So we can then generate the cosine function, and it works just the same. We push the value, we jump to the subroutine, and it will pop the value back off. And we can generate the tangent function, and I've generated this tangent function here. And then go ahead and generate the exponential function. And finally, there's another function here which I generate, which is drawing a line. So we can use our fixed point number system in order to draw a line, and it's not a line between 2 points, it's slightly different. We're going to pick a starting point and a gradient and the number of iterations, and it will draw a line out for us. So that's all of our fixed point subroutines that we have here available to us. If we want, we can add lots more. We could take all of the vector subroutines, which are in integer forms, all of the matrix subroutines, and we could extend them all to the fixed point number system. So this would mean that we would be able to do things, for example, possibly finding the inverse of a matrix, because we've got access to a couple of decimal places, and we can do the division as well. So we could potentially do even looking at things like Gaussian elimination in order to work out inverse matrices. And there's a lot of other things that we could potentially do, but I've deliberately not bothered to do that because, as I said, the whole point of the fixed point number system introduced here is really just as a learning mechanism, so you can see how it works. And you see that computers before we had access to floating point units would work, or some of them would work, with a kind of basic fixed point number system. So that's all here for this. What I'll do is I'll pick out one and we will use it as an example. Now, just to note as well that we can generate lots and lots and lots of different functions, because from the basic core sine, cosine and tangent, we can go ahead and generate a whole load of other functions, and we've got access to generating any function using the Taylor series, and we could generate literally hundreds of functions using the Taylor series. So this is just really just the start of it. So let's have a look at an example. So let's use the example of trying to generate the sine of a number. So the number we're going to use is minus 22.346. It's really quite random. So this is going to be the number in radians. So I'll let this run, so it'll take a minute or so for it to run through and get the correct answer. But let's have a look at it in the graphical calculator. So in the graphical calculator, this is the sine function here, And we're interested in picking a point out here, and the point is minus 22.346. So that's this point here. Okay, now the sine of it is going to be this height, and the correct answer should be 0.34745. Now, we will have a look and see what the correct answer is then within our fixed point number system. So if I bring up the fixed point number system here, so the actual code is written here. So we can see we're going to have the value minus 22.346. So the sign of it should be, as I said, 0.347451. Okay, that's it there. Now that should, in our fixed point number system, give us 0 cross 0058. Okay, so let's have a look and we'll see what the actual answer is that we get. And I'll see if this is finished running yet. I see it's still running up just now. It runs a bit slower because we're obviously recording it. So what we'll do is we'll drop back in and we'll have a look and see what the actual result is. I've already generated this. So we'll go back into the graphical calculator. Now the actual result that we get once this is finished, and I've just put it on there just now, you see it appearing on the screen. So that is the actual answer. So the actual answer is out, okay? No, it's going to be out because we're going to have truncation errors within the actual code, plus the fixed point number system is only accurate to approximately 2 decimal places. So the actual answer that we get is 0.3594, okay? And the answer that we were expecting to get is going to be 0.3474. So we can work out what the actual percentage errors are if we'll have a look at the code again. You'll see here I've put these values at the bottom, maybe a bit small, hopefully you can see it. So the actual result that we get is not 0058, we end up with a result which is 005C. So 005C is in the fixed point number system, and the actual number, the decimal, is 0.359375, so we're 0.011924 out, and this is approximately about a 3% error. Okay, so it's not wildly inaccurate, but it's not really accurate either. We won't get real accuracy until we introduce our floating point number system. So let's have a look and see. Hopefully this will have finished up. So what I'll do is I'll get rid of my image here, I'll fast forward it and we'll have a look at it at the very end, okay? So actually that's it, just finished. The second that I moved my, my image off the screen, it finished. Okay, so let's just go in and we'll have a look just to prove that it does actually do what it says it's doing. So we'll stop the simulation, we'll drop in here, and you can see that the actual answer that we're going to get is in this here, so it's 005C. Okay, so 0058, so we're going to be out by 59, and then it would A, B, and then C. So we would be out by, in effect, 4 places, okay? And that represents about a 3% error in that calculation. But it's interesting, and it's great to see actual mathematical functions being generated. And if we wanted to, we could generate a whole load of different points and then plot them out and generate the sine function, and we could plot the sine function out onto the graphics display as well with one in the machine. There are lots of things we can do with it. Really, there are just masses of things that we can do with this machine now. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.